There are landmarks in our universe not of rock and soil, but of wind and time. They are features carved not by erosion or tectonics, but by the raw, untamed physics of a world. We have grown accustomed to thinking of them as eternal as fixed points in the celestial sea. For centuries humanity has known of just such a landmark, a crimson emblem branded upon the face of a king. It is a storm so vast, so violent and so enduring that it has outlasted every empire on Earth, every dynasty, every human endeavour. It has raged since before we first aimed our crude telescopes toward the heavens, a silent, swirling testament to the sheer scale and power of the cosmos. We are voyaging now across the immense silent gulf that separates our small blue world from the giants of the outer solar system. The journey is long, a silent drift through the velvet blackness measured in hundreds of millions of kilometres. Our destination is a world of superlatives, a planet that could swallow every other object in our solar system save the Sun itself and still have room to spare. You are approaching Jupiter. At this distance it resolves from a brilliant star into a perfect burnished disk, a majestic sphere of ochre, cream and amber. You see the planet not as a static ball, but as a living, breathing entity, its atmosphere churning in magnificent planet-girdling bands. These are not clouds as we know them. They are continent-sized rivers of ammonia ice and unknown chemical compounds flowing at hundreds of kilometres per hour. Jet streams wider than our own planet shear past one another, creating a tapestry of unimaginable turbulence. The scale is so profoundly alien that it defies our terrestrial intuition, forcing us to abandon all familiar frames of reference. Here, weather is not a local event, it is a global geological force. As you draw closer, the planet begins to rotate into view, a stately, almost imperious turn that reveals more of its splendour. And then you see it. At first, it's just a hint of a deeper colour on the horizon, a subtle oval shape nestled between two colossal bands of white cloud. It grows with every passing moment, rising over the limb of the planet like a baleful crimson eye. This is the Great Red Spot. It doesn't look like a storm. It looks like a wound, a planetary abyss staring back into the void. Its colour is a mystery in itself, a shifting palette of salmon, brick red and deep orange, a hue for which we have theories, but no certain explanation. Perhaps it's a result of sunlight breaking down chemicals dredged up from Jupiter's deep hellish interior. Perhaps it's something else entirely, a chemical reaction unique to this one specific place in the universe. The vortex is framed by a delicate swirling collar of paler clouds, like waves breaking against a shore of impossible size. Its immense counterclockwise rotation is visible even from this great distance, a slow, inexorable churn that has captivated and mystified us for generations. To see it is to feel a sense of profound humility, a visceral understanding of your own fleeting existence in the face of something so ancient and so powerful. You're looking at a hurricane so large that it could consume our entire world not just once, but twice over with room to spare. For 3.5 centuries, this celestial leviathan has been the most recognisable feature in our entire solar system, beyond our own moon. It is Jupiter's signature, its soul. Our awareness of this feature began as a ghost in the machine, a fleeting observation in the flickering eyepiece of a primitive telescope. In the 17th century, the great astronomer Giovanni Cassini noted a persistent feature he called the permanent spot. He meticulously tracked its slow march across the face of the gas giant, using it as a cosmic marker to calculate the planet's rotation a day on Jupiter lasting less than 10 of our hours. But what was he seeing? For Cassini and his contemporaries, the concept of a storm of this magnitude was simply beyond comprehension. Was it the peak of a colossal mountain piercing through the dense shroud of Jovian clouds? Or perhaps it was an opening a tear in the atmosphere that offered a tantalizing glimpse into a molten glowing interior. The theories were as wild and grand as the planet itself. For over a century the spot would play a game of cosmic hide-and-seek, vanishing from our view only to reappear decades later, leaving astronomers to wonder if they were seeing the same feature or a new one born in its place. The technology of the time was simply not powerful enough to resolve the debate to truly understand the nature of this enduring mystery. It remained an enigma, a planetary riddle etched in the clouds. It wasn't until the dawn of the great age of space exploration that we began to pull back the veil. The twin Voyager spacecraft, our first robotic emissaries to the outer solar system, swept past Jupiter in 1979, their electronic eyes wide open. For the first time, humanity saw the Great Red Spot not as a faint blurry oval, but as it truly was, a dynamic, terrifyingly complex atmospheric vortex. The images they sent back across 1 billion kilometers of space were nothing short of a revelation. They showed a maelstrom of unimaginable scale and ferocity, a high-pressure system so stable and so vast, it operated on principles we were only just beginning to grasp. It was a rotating column of gas, an anticyclone spinning in the opposite direction of a hurricane on Earth. But this was no terrestrial storm born of warm ocean waters and dissipating over land in a matter of weeks. This was something entirely different, a force of nature unto itself. The physics that drive this behemoth are a symphony of planetary forces. Jupiter has no solid surface to speak of, no land to create friction and rob a storm of its momentum. The Great Red Spot is in a sense a free-floating entity, a kind of gravitational gyroscope trapped between two powerful opposing jet streams. These east-west winds act like colossal conveyor belts feeding smaller storms and eddies into the vortex, providing it with the energy it needs to sustain its furious spin. Its roots extend deep, perhaps hundreds of kilometers down into the crushing pressure of Jupiter's interior, tapping into the immense internal heat that radiates from the planet's core. It is a self-perpetuating heat engine, a storm that feeds itself, a creature born of Jupiter's own primordial energy. The wind speeds at its periphery are astonishing, gusting at over 400 kilometers per hour, far exceeding the most violent hurricanes ever recorded on our own planet. Yet toward its center, there is a strange, eerie calm, the eye of the storm, a region of relative tranquility in the midst of utter chaos. For decades we saw it as the ultimate symbol of cosmic permanence. While continents drifted and mountains rose and fell on Earth, while stars were born and died in the galactic distance, the Great Red Spot simply was. It was a constant, a reassuring presence in a universe defined by change. It became our cosmic anchor, a landmark we used to orient ourselves in the vastness of the solar system. We flew past it. With Pioneer, we photographed it in breathtaking detail with Voyager. We dropped a probe into the atmosphere nearby with Galileo. Most recently, the Juno spacecraft has been swooping over its crimson cloud tops, using its powerful instruments to peer deep beneath the surface, trying to finally understand the secrets of its longevity. Through all of this, the storm endured a silent, swirling giant that seemed to mock our own transient nature. We built models, complex computer simulations that suggested the storm could and should last for hundreds, if not thousands of more years. It was for all intents and purposes immortal. But something is wrong. A profound and unsettling change is taking place, a transformation that has been unfolding quietly, almost imperceptibly for decades. The landmark we thought was eternal is showing signs of its own mortality. Our modern telescopes, both on the ground and in orbit, have given us a power of measurement our ancestors could only dream of. We can now track the storm's dimensions with astonishing precision, year after year, month after month. And the data collected patiently by a generation of astronomers is unambiguous. The Great Red Spot is shrinking. This is not a sudden dramatic event. It is a slow, methodical decay, a quiet fading of a titan. In the late 1800s, when astronomers were able to make the first reliable size estimates, the spot was a vast, elongated oval, stretching more than 40,000 kilometers across. It was wide enough to fit 3 planet Earths side by side. By the time the Voyager probes flew past in 1979, it had already contracted significantly, but it was still a monster easily capable of swallowing 2 Earths. Today, it is a shadow of its former self. The majestic oval has become more circular, and its diameter has shrunk to less than 16,000 kilometers. Now only a single Earth could fit comfortably within its grasp. The crimson giant is wasting away before our very eyes. Its edges appear to be flaking, shedding vast streamers of red material that are caught and torn apart by the surrounding jet streams. The colour, once a deep uniform brick red, now seems more muted, a less vibrant orange. The cosmic timepiece appears to be winding down. This discovery has sent a shockwave through the planetary science community. Our models of its immortality, the ones that predicted its long and stable future, were clearly missing a crucial piece of the puzzle. The very foundation of our understanding of Jupiter's atmosphere is being called into question. We are forced to confront a startling possibility that we might be the last generation of human beings to witness this magnificent spectacle. That a feature that has defined our view of Jupiter for centuries could simply vanish, becoming nothing more than a chapter in old astronomy textbooks. The implications are staggering, and they raise a cascade of urgent, profound questions. What has changed? What fundamental shift is occurring deep within the churning heart of our solar system's largest planet? Is there some unknown mechanism, some subtle change in the atmospheric currents that is now starving the storm of its ancient power? Are we witnessing a natural cyclical process, or is this a terminal decline, the final agonal moments of a celestial giant? The death of the Great Red Spot, should it come to pass, would be more than just the end of a storm. It would be the disappearance of a world icon. But its fading could also be a gift, a unique opportunity. In its decline, the storm may be revealing the hidden dynamics that have powered it for so long. Its final act may be to give up the very secrets we have been chasing for centuries. The race is on to understand what is happening, to decipher the message written in the dying winds of Jupiter. Because in solving the mystery of the shrinking Great Red Spot, we will not only learn the fate of a storm, we will uncover a deeper truth about the life and death of worlds, in a universe defined by ceaseless violent transformation. Where stars are born in fire and die in cataclysmic explosions, we search for permanence. We look for an anchor in the cosmic ocean, something that endures beyond the fleeting span of a human life, beyond the rise and fall of civilizations. For centuries we believed we had found it, not in the silent cratered face of our own moon, nor in the shifting sands of Mars, but in the churning hostile atmosphere of a distant giant. There adrift in a sea of incandescent gas was a feature that seemed to mock the very concept of time itself. A crimson emblem of eternity, a storm that had raged for longer than our own nations had existed. It was a wound in the heavens that would not heal an unblinking eye staring back at us from across the void. We gave it a simple name, a name that belied its magnificent, terrifying nature, the Great Red Spot. And for 300 years its defining characteristic was not its colour or its size, but its stubborn, defiant refusal to disappear. This is the story of that persistence and of the shocking discovery that even monuments built from wind and fury must one day face their end. Our journey to understand this behemoth begins not with supercomputers or robotic spacecraft, but with the fragile flicker of a candle and the glint of polished glass. It begins in the 17th century, a time when the heavens were being ripped open, their ancient celestial certainties shattered by a revolutionary new instrument, the telescope. Through these primitive tubes of wood and leather, a handful of brilliant, obsessive observers were redrawing the cosmos. They saw mountains on the moon, witnessed the phases of Venus, and discovered that Jupiter was not a lone wanderer, but the master of its own miniature solar system, attended by 4 loyal moons. The solar system had suddenly grown deeper, more complex, and infinitely more interesting. In London in the year 1664, the insatiably curious polymath Robert Hooke, a man whose mind darted between the microscopic and the cosmic, turned his modest 36-foot telescope toward the king of planets. He was charting the shadows of its moons as they danced across the planet's face when he noticed something else. A small, faint blemish, a subtle discoloration embedded within one of the planet's pale, striped cloud bands. He described it simply as a spot in the biggest of the 3 obscura belts of Jupiter. It was a fleeting observation, difficult to hold in an eyepiece that swam with distortion and chromatic aberration. The air of London, thick with coal smoke, surely did not help. Hooke saw it, sketched it, and then it was gone, lost in the planet's rapid rotation. Was it a cloud? A shadow? A temporary atmospheric disturbance? He couldn't be sure. His telescope, a marvel for its time, was still a crude porthole into the universe. It revealed just enough to spark the imagination, but not enough to provide definitive answers. The immense distance, the turbulence of Earth's own atmosphere, and the mechanical imperfections of his instrument all conspired to make the heavens a shimmering, unreliable vista. The spot was a ghost, a whisper of something strange happening on another world, but it lacked the substance to be considered a true discovery. It was an astronomical footnote, a curiosity filed away in the annals of the Royal Society, waiting for a more persistent gaze and a clearer sky. That gaze would come just 1 year later from a church tower in Bologna, Italy, where another pioneering astronomer was about to turn this fleeting glimpse into a permanent celestial landmark. Giovanni Domenico Cassini was a meticulous and patient observer, a man who possessed the perfect temperament for the painstaking work of early astronomy. From his vantage point at the Panzano Observatory, using a telescope far superior to Hooke's, he too found the spot. But where Hooke's observation had been a singular event, Cassini's became a dedicated study. Night after night, as Jupiter wheeled across the Italian sky, he tracked the feature. He saw not a static blemish, but a dynamic object carried along by the planet's dizzying spin. The spot would appear at one edge of the planet parade slowly across its vast disk, and then vanish around the other side, only to return with clockwork predictability. This regularity was a revelation. It wasn't just a random cloud. It was an anchored feature, a reliable marker on an otherwise fluid and featureless world. By timing its transit from one limb of the planet to the other, Cassini was able to calculate the length of Jupiter's day, with astonishing accuracy 9 hours and 56 minutes. He had used this strange atmospheric anomaly as a celestial stopwatch. He called it the permanent spot, a name that would echo through the next century, cementing its identity as a fixture of the solar system. For Cassini and his contemporaries, permanent was a relative term, but in the context of the shifting, ephemeral clouds around it, this spot seemed as solid and dependable as a mountain range. It became Jupiter's prime meridian, the reference point from which the rest of the planet's mysteries could be mapped and measured. For over half a century, astronomers followed the permanent spot. They charted its course, noted its subtle changes in colour and intensity, and used it as their guidepost to the Jovian system. It was a familiar friend in the eyepiece, a testament to the order that could be found within the apparent chaos of the cosmos, and then in 1713 it vanished. The observations simply cease. The astronomical records, which for decades had been filled with sketches and notes on its position, fall silent on the matter. The permanent spot was gone. Did it dissipate? Did it fade to a colour indistinguishable from the surrounding clouds? Or did the astronomers of the early 18th century, perhaps preoccupied with other celestial pursuits, simply stop looking for it? This gap in the historical record creates a profound and tantalising mystery that endures to this day. Was the storm observed by Hooke and Cassini the very same entity we see today? Or was it a predecessor, a similar but distinct storm that lived and died only to be replaced by a successor over a century later? The life of the Great Red Spot might not be one continuous, unbroken thread stretching back to the dawn of the telescopic age. Instead, its history may be a story of dynasty of great storms rising and falling in the same turbulent patch of atmosphere, with the current monarch taking the throne long after the first had abdicated. For 118 years, the great eye of Jupiter appeared to be closed. The silence was finally broken in 1831. An amateur astronomer in Germany named Samuel Heinrich Schwabe, a man whose main passion was obsessively counting sunspots, was sketching Jupiter when he depicted a clear, distinct and decidedly oval-shaped feature in the planet's south equatorial belt. He hadn't set out to find it, he had simply stumbled upon it. Soon, others began to confirm the sighting. The spot was back, or a spot was back. By the 1870s, with the advent of larger and more powerful telescopes, its presence was undeniable. It blazed with a distinct brick-red hue, a stark and dramatic contrast to the pale yellows, ochres and whites of the surrounding cloudscape. It was during this period that it earned its modern, more evocative title, the Great Red Spot. No longer a subtle discoloration, it was now a spectacle. It became the planet's defining characteristic, an object of intense scientific scrutiny and public fascination. Its rediscovery in the 19th century transformed it from a historical curiosity into a living, breathing enigma. It was no longer just a tool for measuring rotation, it was now the single greatest meteorological puzzle in the solar system. A new generation of astronomers armed with the tools of spectroscopy and photography would now attempt to answer the fundamental question that had eluded their predecessors for 2 centuries. What in God's name was? To even begin to comprehend the challenge they faced, we first have to grapple with the sheer mind-altering scale of this object. Calling it a storm is a profound understatement. It is a meteorological event on a scale so vast that it beggars the human imagination. When it was first being studied in detail in the late 1800s, this single atmospheric disturbance was large enough to swallow the planet Earth 3 times over with room to spare. Imagine a hurricane so colossal that its eye wall could contain our entire world from pole to pole. Then imagine that hurricane flanked by 2 more identical planets, all fitting comfortably within its swirling crimson borders. This is not science fiction. This was the physical reality of the Great Red Spot. The winds tearing around its perimeter were measured at over 400 miles per hour speeds that would vaporize any terrestrial structure scouring continents down to bedrock. It is an anticyclone, a high-pressure system spinning counterclockwise in Jupiter's southern hemisphere. But unlike the gentle high-pressure zones that bring clear skies to Earth, this is a maelstrom of unimaginable power. It is a cosmic engine whose energy output dwarfs the combined force of every hurricane, typhoon, and cyclone ever recorded in human history. It is a celestial blowtorch dredging up material from deep within Jupiter's mysterious interior, and churning it in a vortex that has lasted for centuries. This is not weather as we know it. This is geology on a gaseous scale, a tempest so large and powerful that it has its own climate, its own internal structure, and its own indomitable will to survive. And that survival was the core of the mystery. On Earth, a hurricane is a fleeting thing. It is a heat engine born from a very specific set of conditions, a vast expanse of warm ocean water providing the moisture and energy that fuel its ascent. Its life is a frantic, desperate race against its own destruction. The moment it makes landfall, its connection to that warm water is severed. The friction from the land tears at its foundations, robbing it of momentum, starving it of power. Within days, even the most monstrous Category 5 hurricane is reduced to a whisper of rain and cloud. It dies because its fuel source is finite, and its path inevitably leads to its own demise. But Jupiter offers no such release. Jupiter has no land. It has no solid surface anywhere to act as a brake. It is a bottomless abyss of gas and liquid, a world without shores. So what could possibly sustain a storm like the Great Red Spot, without a warm ocean to feed it? What is its engine? And without a continent to break it apart, what could ever stop it? For scientists in the 19th and early 20th centuries, this was a paradox of the highest order. The storm's very existence seemed to violate the fundamental principles of meteorology as they understood them. It was as if they had discovered a fire that had been burning for 300 years without any discernible source of fuel. The first attempts to explain this impossible object were a testament to the ingenuity and the limitations of the science of the day. They were grappling with a phenomenon completely outside of their terrestrial experience, and so their theories were a blend of astute observation and wild, creative speculation. One of the earliest ideas proposed that the Great Red Spot wasn't a storm at all, but something solid. Perhaps some thought it was a colossal floating island, a kind of planetary-sized raft made of some unknown material bobbing on a sea of liquid hydrogen. This theory accounted for its persistence, but it failed to explain its fluid, swirling nature and its ability to change shape and colour. Another more dramatic theory cast the spot as an active gargantuan volcano. Proponents of this idea imagined it as the mouth of a permanent eruption, belching up heated material from Jupiter's molten core. The red colour, they argued, was the glow of incandescent rock and exotic chemicals dredged up from the planet's infernal depths. This was a compelling and wonderfully planetary vision, but it struggled to align with the physics of a gas giant. There was no solid crust from which a volcano could erupt. The pressure and temperature deep inside Jupiter are so extreme that rock and metal would behave in ways we can barely model, let alone form a stable volcanic caldera. A more subtle and scientifically grounded theory suggested the spot was not something rising up but a window looking down. This was the hole in the clouds hypothesis. It proposed that Jupiter's atmosphere was layered like a terrestrial sky, with different cloud decks made of different chemicals at different altitudes. The visible surface, they theorized, was a high-altitude layer of pale ammonia ice crystals. The Great Red Spot in this view was a persistent cyclone-induced clearing in this upper deck, a hole through which we were peering into a deeper, warmer, and inherently redder layer of the atmosphere below. The colour wasn't from a volcano, but from complex organic molecules, or perhaps compounds of sulfur or phosphorus cooked by the planet's internal heat and exposed to sunlight. This theory was elegant and explained the colour well, but it still struggled with the core problem of longevity. What could possibly keep a hole in a planet's atmosphere open for 3 centuries? Any breach should be quickly sealed by the surrounding winds and the natural churning of the atmosphere. Each of these early theories, while ultimately incorrect, represented a crucial step forward. They forced scientists to stop thinking about Jupiter in earthly terms and to start imagining a world governed by a completely alien set of physical rules. They were learning that to solve the riddle of the Great Red Spot, they would have to invent a new kind of meteorology. The conceptual breakthrough came with the growing understanding of fluid dynamics. As the 20th century progressed, scientists began to model Jupiter not as a world with weather, but as a world that is weather. It is a sphere of spinning fluid, a natural laboratory for forces that dwarf anything we experience on Earth. They realized the Great Red Spot was not an object or a hole, but a self-sustaining dynamic system, a vortex. Specifically, it is a colossal anticyclone, a region of high atmospheric pressure. On Earth, air flows out from high-pressure centers, creating calm weather. On Jupiter, the planet's immense gravity and blistering rotational speed, a day lasts less than 10 hours, twist this outflow into a furious contained spiral. This immense rotational force, known as the Coriolis effect, is the master architect of Jupiter's atmosphere, stretching weather systems into the planet's famous horizontal bands and belts, and it is the force that gives the Great Red Spot its life. But even this understanding wasn't enough. A vortex, no matter how large, should still bleed energy to its surroundings. Friction, even in a gaseous environment, should slowly grind it to a halt. The storm should mix with the adjacent cloud bands, lose its distinct identity, and fade away over time. Yet it did not. Something was feeding it. Something was protecting it. The answer, it turned out, lay not within the storm, but on its borders. The Great Red Spot is perfectly and precariously positioned between 2 of Jupiter's most powerful jet streams, which scream past it in opposite directions at hundreds of miles per hour. The jet stream to its north flows westward, while the one to its south flows east. These 2 atmospheric rivers act like a pair of immense planetary scale rollers, spinning the Great Red Spot between them, like a giant captive ball bearing. They are the walls of its prison, preventing it from meandering north or south into different latitudes where it would be torn apart. But they are also its source of strength. The chaotic, turbulent energy generated at the boundary where the storm grinds against these jet streams is constantly feeding momentum back into the vortex, helping it to maintain its ferocious spin. Furthermore, this unique position turns the Great Red Spot into a predator. Smaller storms, eddies and vortices that form in the surrounding zones are swept along by the jet streams and are often funneled directly into the path of the behemoth. We have watched through our telescopes and the eyes of our robotic probes as the Great Red Spot consumes these lesser storms, swallowing them whole. Each collision is a meal, a transfusion of energy and momentum that revitalizes the ancient tempest, healing its losses and ensuring its continued reign. It is a gravitational gyroscope locked in place and spun by the planet itself, a meteorological vampire that sustains its immortal life by feeding on its own children. By the time humanity prepared to take its first steps into space, the Great Red Spot had been elevated from a scientific curiosity to a cultural icon. It was Jupiter's signature, as recognizable as Saturn's rings. For generations of astronomers, both amateur and professional, it was a constant, a reliable friend in the night sky. In a solar system where comets came and went, where meteor showers peaked and faded, and where the surface of Mars was obscured by seasonal dust storms, the spot was always there. It was a testament to the power of nature, on a scale we could barely comprehend, a symbol of endurance. It had become the solar system's Rock of Gibraltar, an unyielding monument against which the passage of time seemed to have no effect. It had survived the scientific revolution, the industrial revolution, and the dawn of the atomic age. It raged while empires on Earth rose and crumbled into dust. This perception of permanence became its legend. It was the one thing in the chaotic swirl of the solar system that we thought we could count on a crimson anchor holding fast in a sea of change. For over 300 years of human observation, it was the definition of immutable, a grand celestial machine that could not be broken. And then, with the dawn of a new millennium, our ever more powerful telescopes and our robotic emissaries sent to orbit, the giant began to tell us a different story. The data they sent back across the hundreds of millions of miles of empty space was unambiguous and deeply unsettling. Our eternal storm, our symbol of cosmic persistence, was beginning to falter. The unblinking eye of Jupiter was starting to close. We had spent 3 centuries marvelling at its refusal to die, and were now forced to confront an even more profound mystery, the shocking possibility of its demise. The monument was crumbling. For centuries it had been a smudge in a lens, a crimson ghost, haunting the periphery of our understanding. It was a feature of Jupiter, yes, but more than that, it had become a feature of our own cosmic imagination, a symbol of the eternal, the unchanging, the impossibly vast. Then we left the cradle. We built emissaries of silicon and gold extensions of our own senses and hurled them across the 600 million kilometre gulf. Humanity was about to get its first true look. The twin Voyager spacecraft launched in the summer of 1977 were more than probes. They were our species' first audacious knock on the doors of the outer solar system. And as Voyager 1 screamed past Jupiter in March of 1979, it transformed that distant static smudge into a living, breathing world of terrifying beauty and unimaginable violence. For the very first time, we saw the Great Red Spot not as an object, but as a place. The stream of data returning to Earth was a revelation, painting a portrait of a storm so complex it defied terrestrial language. This was no simple cyclone. It was a high-pressure anticyclone, a rotating continent of gas so enormous you could drop 3 Earths into it with room to spare. The images revealed a maelstrom of staggering intricacy. We saw it as a colossal churning vortex, a cosmic whirlpool spinning counterclockwise with a furious elegance. Its edges were not smooth but scalloped and turbulent, a chaotic interface where the spot's 400 km/h winds collided with the surrounding jet streams that screamed past in opposite directions. It was a planetary gear grinding against the atmosphere of Jupiter itself. Voyager's cameras, our new eyes showed us smaller white-coloured storms themselves the size of terrestrial continents, being swept into the crimson behemoth's path. They would orbit the edge for a time like terrified ships caught in a whirlpool before being unceremoniously swallowed, their substance devoured and assimilated into the larger storm's incomprehensible energy budget. The colours themselves were a mystery we were only beginning to probe. No longer a simple red, the palette was a swirling tapestry of crimson salmon, deep orange and pale cream, suggesting a complex high-altitude, atmospheric chemistry, being cooked by unseen radiation from above and driven by heat from below. The spot was a celestial blast furnace, dredging up materials from Jupiter's deep interior and exposing them to the harsh, ultraviolet light of the sun, creating exotic compounds we could only guess at. In those breathtaking flyby images, the Great Red Spot seemed more invincible than ever. It was the undisputed king of a kingly planet, a monument to permanence. The data Voyager sent back reinforced every assumption we had ever made about its stability. Its sheer momentum, its monstrous scale, its apparent ability to feast on smaller storms to sustain its own life, all of it pointed to a feature that had been there for centuries and would surely be there for millennia more. It was a force of nature so profound it seemed to operate outside the normal laws of decay. But a fleeting glance, even one as revolutionary as Voyager's, is not the same as a sustained watch. The next chapter in our exploration required a deeper commitment. It required us to move in. That commitment arrived in the form of a mission named for the very man who first charted Jupiter's moons, Galileo. Launched in 1989, the Galileo spacecraft was not designed for a quick hello. Its destiny was to become the first artificial moon of Jupiter to enter into a long looping orbit and become a permanent resident, a silent robotic witness to the planet's daily life. After a 6-year journey upon its arrival in 1985, Galileo gave us a perspective Voyager never could time. Instead of snapshots, we began to assemble a movie. We watched the Great Red Spot not just as a static portrait, but as a dynamic, ever-changing weather system. Galileo's instruments were more advanced, capable of peering deeper. seeing in wavelengths of light invisible to the human eye. It measured temperatures, charting the cold core of the storm and the warmer annulus at its periphery. It dropped a probe into Jupiter's atmosphere, a kamikaze messenger, that sent back precious data on wind speeds and atmospheric composition before being crushed and vaporized by the immense pressures below. We were no longer just looking at the clouds. For a brief fiery moment we had touched them. Galileo's long patient vigil revealed the storm's true character. It was a gravitational gyroscope spinning with such colossal mass and velocity that it stabilized itself against the planet's chaotic jet streams. It was a planetary heat engine drawing its power not from the sun as Earth's storms do, but from Jupiter's own internal furnace, the primordial heat left over from its formation 4.5 billion years ago. The mission confirmed the storm's awesome power, yet in the volumes of data collected over its 8 years of service, the first quiet whispers of a different story began to emerge. Scientists comparing Galileo's precise measurements to Voyager's older baseline noticed subtle inconsistencies in its shape. It seemed less perfectly elliptical, perhaps a little more rounded. The intricate turbulence at its edges seemed to behave differently. These were tiny, almost imperceptible shifts, the kinds of data points that are easily dismissed as measurement errors or temporary fluctuations. At the time, they sparked little more than academic curiosity and minor footnotes in papers, celebrating the storm's grandeur. The prevailing view held firm the spot was eternal. These were just the transient moods of a giant. But to truly solve a mystery of this scale, you need more than a fleeting glance, or even an 8-year orbit. You need a watchtower. You need an unblinking eye, one that can stare uninterrupted for decades. That eye was waiting for us, not in orbit around Jupiter, but in orbit around Earth. The Hubble Space Telescope, poised high above the blurring distortions of our own atmosphere, became our permanent lookout post on the cosmos, and year after year it turned its magnificent mirror toward Jupiter. This is where the story began to pivot. This is where the quiet whispers grew into a steady, insistent murmur. Through programs like the Outer Planet Atmosphere's Legacy or Opal Hubble, began to provide something unprecedented in the history of astronomy, a consistent high-fidelity long-term health record for Jupiter's atmosphere. Every year, scientists would get a new crystal-clear portrait of the entire planet. And by placing these portraits side by side, a shocking narrative began to unfold. The change was no longer subtle. It was no longer debatable. It was happening right before our eyes. The Great Red Spot was shrinking. And not just shrinking, but shrinking dramatically. The data was undeniable. When the Voyager probes flew by in 1979, the storm was a majestic oval spanning over 23,000 kilometers wide, enough to comfortably fit 2 Earths side by side. By the time Galileo was studying it in the mid-1990s, it had lost some of that impressive width. But Hubble's annual checkups revealed the trend was accelerating. By 2012, it was noticeably smaller. By 2014, astronomers were stunned to see that its shape had changed fundamentally. It was no longer a grand oval. It was becoming a circle. Its longitudinal dimension had been cut nearly in half. The storm that once held 3 Earths could now barely contain one. The numbers were stark. Each year, Hubble's measurements showed the spot's boundary was contracting by nearly 1,000 kilometers. It was as if a cosmic string was being pulled tight around it, squeezing the ancient storm into a smaller, more compact and more circular form. Furthermore, its majestic crimson colour, once so deep and uniform, was beginning to fade, becoming a more diffuse, watery shade of orange. The invincible monument was beginning to crumble. The scientific community, once so certain of the storm's permanence, was thrown into a state of profound cognitive dissonance. It was like watching a mountain erode into a hill in the span of a single generation. The very foundation of what we thought we knew about planetary dynamics was shaken. A fierce and urgent debate erupted, splitting researchers into 2 main camps, each trying to explain the unbelievable transformation we were witnessing. One school of thought argued for history for cycles. They contended that what we were seeing was not a death, but a breath. Perhaps the Great Red Spot has always waxed and waned like this over cycles spanning centuries or even millennia. We had only been observing it with precision for a few short decades, an infinitesimal sliver of its potential lifespan. From this perspective, the storm wasn't dying, it was merely exhaling. It might have been even larger in the 1700s and smaller in the 1500s. We had simply caught it in a period of contraction. They pointed to historical drawings from the 1800s that depicted a much larger, more elongated storm, suggesting that shrinkage was a long-term trend, not a recent crisis. This was the conservative, reassuring hypothesis the system was stable, and we were just witnessing a normal fluctuation. But another more alarming camp emerged. They argued that the rate of change was too fast, too dramatic to be cyclical. Something fundamental had shifted in the atmospheric engine that powered the storm. The change wasn't just in size, but in character. The storm's internal wind speeds paradoxically seemed to be increasing, even as its perimeter shrank like a figure skater pulling in their arms to spin faster. This suggested a system under stress, a system losing its equilibrium. These scientists proposed that the very structure of Jupiter's atmospheric bands, the jet streams that corralled and fed the storm, might be changing. Perhaps a key source of energy, a river of atmospheric momentum that had nourished the vortex for centuries, was now being diverted. Or maybe the storm was suffering from a kind of starvation, failing to absorb the smaller storms that once served as its fuel. Hubble's images seemed to support this, showing smaller vortices now zipping past the spot without being drawn in and consumed as they had been in Voyager's day. The debate raged in the halls of universities and at planetary science conferences. For one side to suggest the storm was dying was alarmist, a conclusion drawn from an impossibly short baseline of data. For the other to assume it was a cycle was complacent, a failure to recognise the signs of a profound and possibly terminal transformation. The assumption of invincibility, an idea that had stood for 300 years, had been shattered in less than 30. Our robotic explorers had taken us close enough to finally read the Book of Jupiter, only for us to discover that its most famous chapter might be nearing its end. We had arrived at the bedside of a Titan, watching its pulse weaken, its breathing grow shallow, unable to agree on the diagnosis. Was this a temporary fever, or the final throes of a life measured in centuries? The meticulous monitoring had answered the question of what was happening. The great red spot was contracting, changing, perhaps even unravelling. But it had opened up a far deeper and more terrifying mystery, a question that would demand a new generation of exploration to answer. Not just what, but why. To find that answer, we would need to look beyond the crimson clouds, beyond the simple observations of size and shape. We would have to probe the very heart of the storm itself, and decode the invisible forces that gave it life, and now seemed to be taking that life away. The giant was faltering, and the clock was ticking. For generations we had been spectators watching from the distant shores of our solar system. Our telescopes, even the most powerful, were still staring across an abyss of hundreds of millions of kilometres. We saw the symptom, a shrinking, fading icon, but the cause remained shrouded, locked away beneath an impenetrable veil of ammonia clouds. The data we gathered was like a physician trying to diagnose a patient from across a crowded room, relying only on sight. We knew the patient was ailing, but the internal mechanics of the disease were a complete mystery. We needed to get closer, we needed to put a stethoscope to the heart of the giant. Then, in the summer of 2016, humanity sent a true interloper. Not a fleeting visitor like the Voyagers, nor an orbiter held at a respectful distance like Galileo, but a dedicated investigator poised to dive headfirst into the very heart of the maelstrom. Its name was Juno. Forged in clean rooms on Earth, hurled across the solar system on a 5-year journey, this 3-armed probe was more than a machine. It was our proxy, our avatar, a marvel of engineering designed for one audacious purpose: to unmask Jupiter. Juno would not trace a safe equatorial path around the planet's waste. Instead, its destiny was to perform a series of breathtaking, terrifying plunges, screaming over the poles in a looping petal-like dance. Each 2-hour pass from the North Pole to the South was a surgical incision into the most violent radiation environment in the solar system, a fleeting chance to gather data no previous mission could even dream of. And on July 11th, 2017, the moment came. After a year of mapping Jupiter's poles and magnetic field, Juno's trajectory was finally aligned. For the first time in human history, a spacecraft was about to fly directly over the Great Red Spot. In the control rooms at the Jet Propulsion Laboratory, There was a palpable tension, a fusion of excitement and anxiety. Years of planning, billions of miles of travel, all culminating in a few minutes of critical data acquisition. As Juno barreled towards its target at over 130,000 miles per hour, its instruments shielded behind a vault of titanium began their work. The high-resolution eye of Juno Cam opened its gaze, fixed on the swirling crimson abyss below. But the most important discoveries would come not from what Juno could see, but from what it could sense. Imagine possessing a form of sight that could pierce through the densest fog not with light, but with warmth. This is the revolutionary gift of Juno's microwave radiometer, or MWR. The MWR is not a camera. It is a set of 6 antennas, each tuned to a different microwave frequency. These frequencies act like keys, unlocking different layers of Jupiter's atmosphere. The shorter wavelengths peer just below the visible cloud tops, while the longest, most powerful wavelengths can penetrate hundreds of kilometers down deep into the planet's crushing interior, where pressures are 1,000 times greater than on Earth's surface. It gave us a way to perform a kind of atmospheric tomography, creating a 3-dimensional map of the storm's hidden anatomy layer by agonizing layer. As the first MWR data streamed back to Earth, a process that took over 45 minutes at the speed of light, the scientific community held its collective breath. What they were about to witness was the scientific equivalent of a tectonic shift. The centuries-old assumption had been that the Great Red Spot, for all its majesty, might be a relatively shallow phenomenon. A vast but superficial weather event, a skin-deep blemish on the face of a gas giant. The models built on long-distance observation often depicted it as a kind of colossal atmospheric pancake floating serenely in the upper cloud decks. Juno's microwave eyes shattered that illusion forever. The data was unequivocal, startling in its clarity. The Great Red Spot was no pancake. It was a monster of unbelievable depth. Its roots, its anchor, plunged down, down, down into the darkness of Jupiter's troposphere. 350 kilometers, perhaps as far as 500. That's the distance from London to Paris, driven straight down into a hurricane. This storm was deeper than the International Space Station's orbit is high. It wasn't just a storm on Jupiter, it was a storm of Jupiter, an integral part of the planet's structure, a monolithic column of swirling gas, a true atmospheric leviathan. This single revelation fundamentally recontextualized everything. It explained the storm's incredible longevity. A shallow storm would have been shredded and dissipated by the planet's savage jet stream centuries ago. But this was a cosmic anchor. Its immense depth gave it thermal inertia and angular momentum on a scale we had scarcely imagined. It was a self-sustaining gravitational gyroscope, its base locked into atmospheric layers far below the chaotic weather we see on the surface, drawing its energy not just from the winds around it, but from the heat percolating up from Jupiter's deep, mysterious interior. You are not looking at a mere weather pattern. You are looking at a planetary organ, a structure so vast and deep that its base experiences pressures and temperatures that would liquefy rock. And with Juno's repeated passes, we confirmed not only its depth, but the terrifying reality of its decline. JunoCam's images taken from altitudes as low as a few thousand kilometers were unlike anything we had ever seen. They were not sterile scientific photographs. They were intimate, terrifying portraits of a dying god. Where Hubble saw a shrinking oval, Juno saw the brutal, messy process of its dissolution. We could see the edges fraying not smoothly, but in violent, filamentous tendrils of gas being torn away by the surrounding jet stream, a river of wind flowing at 300 miles per hour. These crimson streamers, some larger than entire countries on Earth, were being peeled off the main vortex like flesh from a wound. We witnessed smaller storms which in the past might have been absorbed as fuel now colliding with the spot's periphery, and seeming to chip away at its structure, carrying off its energy and mass in a slow, agonizing process of attrition. The storm wasn't just shrinking, it was being actively dismantled. The high-resolution data confirmed with chilling precision the accelerated rate of change. The grand, majestic oval was becoming more circular, more chaotic, its internal structure losing its coherence. It was losing its fight. This was the turning point. The confirmation of its depth, coupled with the high-resolution evidence of its violent decay, shifted the entire paradigm of the investigation. The The question was no longer the simple observational query, is it shrinking? Now armed with an understanding of its three-dimensional structure, we could finally ask the deeper, more meaningful question. Why is it dying? The focus pivoted from monitoring a decline to diagnosing its cause. The global community of planetary scientists now equipped with this revolutionary data set began to formulate new, far more detailed hypotheses, moving beyond speculation and into the realm of testable physics. The era of distant observation was over. The era of forensic atmospheric science had begun. One of the first and most compelling new theories centered on a crisis of nourishment. For centuries, we believed the Great Red Spot maintained its colossal energy by acting as a cosmic predator, consuming a steady diet of smaller anticyclonic vortices that were swept into its path. These smaller storms acted like fuel pods, injecting fresh momentum and energy into the system, counteracting the natural forces of dissipation. But Juno's detailed mapping of Jupiter's intricate jet streams and zonal flows suggested that this vital supply chain might be breaking down. We began to model whether subtle shifts in these atmospheric rivers were now diverting the smaller storms away from the Great Red Spot. Is it possible that the giant is quite simply starving? The intricate dance of Jupiter's weather bands, once a reliable conveyor belt of fuel, might have changed its rhythm, leaving the storm isolated and deprived of the very energy it needs to survive its own internal friction. It may be dying not from a sudden cataclysm, but from a slow, inexorable famine. A second, more profound hypothesis emerged from the MWR data itself. The discovery of the storm's deep roots pointed to a powerful connection with the planet's internal heat engine. Far below the clouds, Jupiter's interior glows with heat left over from its formation, a primordial furnace that drives much of its atmospheric dynamics. The Great Red Spot, this theory proposes, is not just a passive structure being pushed around by winds. It is an active convective tower, a massive atmospheric heat pipe channeling that internal energy upwards to the visible cloud tops. If this is true, then its decline might not be due to external factors at all. The problem could be internal. The very conduit that has powered it for centuries could be weakening or becoming blocked. Perhaps changes in the deeper atmospheric layers invisible to us before Juno are now choking off its energy supply from below. The storm's furnace could be sputtering out its mighty engine, losing its connection to the planetary powerhouse deep within. We are no longer just studying weather. We are studying planetary geology, a deep, fundamental change in how Jupiter vents its internal heat to space. A third complementary theory focused on the brutal mechanics of its erosion, which JunoCam was now documenting in exquisite detail. Scientists began to call it the flaking hypothesis. The imagery showed that the interaction between the storm's outer edge and the surrounding high-speed jet streams was far more violent than previously thought. These are not gentle currents. This is a perpetual grinding collision zone. The thinking is that as the storm has naturally shrunk over time, its rotational velocity has likely increased just as a figure skater spins faster when she pulls her arms in. This faster rotation creates even more turbulence and friction at its boundary. It's a vicious feedback loop. The storm shrinks so it spins faster. It spins faster so it sheds more material at its edges. It sheds material so it shrinks further. Juno allowed us for the first time to quantify the scale of these flaking events, to measure the sheer tonnage of gas being ripped away with each interaction. We are watching a coastline of atmospheric rock being eroded by a relentless sea, and the erosion is accelerating. These new hypotheses were not mutually exclusive. The grim reality is that all three could be happening simultaneously. The storm could be starving from without decaying from within, and being torn apart at its edges, a multi-front war against the fundamental laws of thermodynamics. In conference halls and university departments around the world, the Juno data became the new gospel. Scientists built incredibly complex computer simulations, feeding them the new parameters of the storm's depth and thermal structure. They could now model the flow of energy with unprecedented fidelity testing, whether a lack of food or a disruption in its internal heat flow would produce the shrinking and flaking we were observing in real time. For every pass, Juno made a torrent of new information, flooded the system, refining the models, challenging old assumptions, and sparking fierce, passionate debate. The mystery of the Great Red Spot was no longer a distant astronomical curiosity. It had become one of the most active and exciting puzzles in planetary science, a dynamic problem unfolding right before our eyes. Juno had given us the missing dimension. It had taken a flat two-dimensional portrait and revealed the complex breathing three-dimensional sculpture beneath. We could now see that the storm was not just a feature, it was a deeply integrated piece of planetary machinery. And with this profound revelation, the diagnosis of its decline became infinitely more complex and infinitely more important. Its death was not simply the end of a long-lived weather pattern. It was a symptom of a much larger, more fundamental change in the atmospheric engine of the largest planet in our solar system. The question now was not just how it was dying, but what its death would unleash. What happens when a storm bigger than Earth and anchor embedded deep within the planet's soul finally lets go? The data was pointing towards an endgame, but the final act of this centuries-long drama remained terrifyingly unwritten. So the Titan is wounded, its great eye no longer glaring with the same ancient fury. For generations we have stared back at that crimson vortex, a storm so vast it could swallow our world whole, and we assumed it was a permanent feature of the heavens as eternal as the planet it adorned. But the clock is ticking, and the centuries-old wound is closing. The evidence is undeniable, etched in the pixels of our most powerful telescopes. The question that now echoes through the halls of planetary science, the puzzle that consumes theorists and observers alike, is no longer if the Great Red Spot is diminishing. It is why. What cosmic force, what subtle change in the heart of a gas giant could possibly be taming a tempest that has raged since before we even built the ships that crossed our own oceans? The answer we are discovering is as complex and layered as Jupiter itself. There is no single culprit, no simple explanation for the fading of a legend. Instead, we are faced with a web of interconnected possibilities, a grand cosmic detective story with 4 prime suspects, each with a compelling motive for the slow, methodical murder of a monster. The first and perhaps most intuitive hypothesis casts the blame on external assailants. Imagine the Great Red Spot not as a solitary monolith, but as a colossal predator navigating a chaotic, crowded jungle. For its entire existence, it has been surrounded by a swarm of smaller, though still continent-sized storms. These anticyclones, like the red spot itself, are high-pressure systems spinning in the opposite direction of their cyclonic brethren. For centuries we watched them dance around the edges of the behemoth, sometimes getting close, only to be deflected by its immense power, like small boats skirting the edge of a monstrous whirlpool. But our modern observations, with the piercing gaze of Hubble and the intimate perspective of the Juno spacecraft, have revealed a far more violent and consequential relationship. We see these smaller storms, these ambitious vortices, not just skirting the edge, but directly colliding with the Great Red Spot. The footage is mesmerizing, a display of atmospheric violence on an unthinkable scale. An oval the size of a terrestrial ocean slams into the flank of the main storm. For a moment it seems to be absorbed, swallowed whole by the Crimson Giant. But the interaction is not a simple act of consumption. It is a brawl. As the smaller storm is drawn in, it unleashes a flurry of turbulence. It sheds its own energy and momentum into the larger system, disrupting the organized majestic flow of the Great Red Spot's winds. Scientists have given this phenomenon a chillingly descriptive name: flaking. We see vast streamers of red cloud material, hundreds of thousands of miles long, being peeled away from the storm's outer layers, torn loose by the collision. These are not gentle caresses, they are body blows, each one landing with the force of 1,000 terrestrial hurricanes. For a time it was thought the red spot was feeding on these smaller storms, that these collisions were a source of energy, a way for the giant to sustain itself. But a new school of thought proposes the exact opposite. These interactions are not a feast, they are a parasitic attack. The smaller storms act as atmospheric shredders, nibbling away at the edges of the Great Red Spot, draining its momentum and carrying away its substance piece by agonizing piece. They are a swarm of piranhas slowly, relentlessly stripping the flesh from a leviathan. With each collision, a little more of the giant's angular momentum, its lifeblood, is sapped away. A little more of its well-defined structure is thrown into chaos. Over the course of decades, these thousands of tiny cuts could collectively become a mortal wound, gradually eroding the storm's defenses, shrinking its perimeter, and quieting its roar. Yet this compelling theory comes with its own nagging question. These smaller storms, these atmospheric aggressors, are not a new phenomenon. They have been a feature of Jupiter's cloudscape for as long as we have been watching. The Great Red Spot has weathered their assaults for centuries. So why now? Why would these encounters suddenly become so much more effective, so much more damaging? Has the frequency or intensity of these smaller storms increased? Or has the Great Red Spot itself, for some other deeper reason, lost its resilience, its ability to fend off attackers it once shrugged off with ease? The theory of death by 1,000 cuts is powerful, but it suggests the victim may have already been weakened by a more insidious internal ailment. This leads us to our second suspect, a force more subtle, but perhaps even more fundamental. The Great Red Spot does not exist in a vacuum. It is a feature embedded within Jupiter's spectacular and fiercely organised atmosphere. The planet is wrapped in a series of powerful jet streams, bands of wind that scream east and west at hundreds of miles per hour. Two of these jets form the northern and southern boundaries of the Great Red Spot. They are not merely neighbours, they are the storm's shepherds. Think of them as two colossal rivers of wind flowing in opposite directions. The storm itself is like a giant spinning log caught between them. The shear between these two jets provides the vorticity, the rotational energy that has helped to spin this colossal vortex for centuries. They confine it, they energise it, they maintain its very existence. For the storm to remain stable, this delicate balance must be preserved. The jets must remain at the correct latitude, flowing with the correct velocity. They are the walls of the canyon that guide the river. But what if those walls began to move? What if the very structure of Jupiter's zonal jets is changing? Planetary scientists are now exploring a startling possibility that the southern jet stream, the one that cradles the red spot's lower half, may be migrating. Even a subtle shift northward, a change of just a degree or two in latitude over a century, could have catastrophic consequences for the storm. It would be like slowly closing the gap between the two riverbanks, squeezing the spinning log, disrupting the flow that sustains it. Furthermore, there is evidence that the winds within this southern jet are slowing down. If the jet loses speed, it delivers less of a rotational kick to the storm. The engine that has been feeding the vortex is beginning to throttle down. This could initiate a slow, cascading failure. As the storm receives less energy from the jets, its own winds begin to decelerate. As its winds slow, its ability to resist the flaking from smaller storms diminishes. It becomes more vulnerable to those external attacks we just witnessed. The two theories begin to intertwine, painting a more complete and more tragic picture. But this too begs a deeper question. What could cause Jupiter's fundamental atmospheric structure, its global jet streams, to change? These are not weather patterns in the way we understand them. They are expressions of the planet's deep interior dynamics, driven by a combination of its rapid rotation and the powerful convection of heat from its core. To alter a jet stream is to alter the very heartbeat of the planet. And so, we must look deeper still past the sunlit clouds of ammonia and water, down into the crushing darkness of the planet's abyssal heart. Here we encounter our third and most profound suspect. The planet's internal heat engine is failing its most famous child. Jupiter is not a cold dead ball of gas. It radiates more than twice the amount of heat into space than it receives from the distant sun. This is primordial heat, a relic from the planet's violent formation 4.5 billion years ago, supplemented by ongoing gravitational contraction. This internal furnace drives powerful convective currents. Imagine colossal plumes of hot gas rising from the depths, where pressures are millions of times that of Earth's atmosphere. As this gas rises, it expands and cools, eventually sinking back down in a continuous planet-spanning cycle. This process, known as convection, is the ultimate engine for all of Jupiter's weather, including the jet streams, and many scientists believe the Great Red Spot itself. The prevailing model suggests the storm is the surface manifestation of a gigantic, persistent upwelling plume, a celestial blowtorch of heat rising from thousands of miles below. This continuous flow of warm, buoyant gas provides the raw thermal energy that the storm converts into the kinetic energy of its ferocious winds. It is the fuel that has kept the fire burning for so long. If this model is correct, then the storm's slow decline could be a sign of something truly fundamental changing within Jupiter. Perhaps the specific plume of heat that feeds the Great Red Spot is weakening. The flow of energy from the deep interior could be fluctuating, or perhaps its path to the surface has been partially obstructed or diverted by some change in the deeper atmospheric layers. It would be like turning down the gas on a cosmic stove. The flame once roaring would begin to flicker and shrink, losing its intensity, its colour and its reach. This is by far the most difficult hypothesis to prove. We cannot send a probe deep into Jupiter's interior to measure this heat flow directly. The pressures and temperatures would crush and vaporise any machine we could build. Our view is frustratingly limited to the uppermost cloud layers. We are like doctors trying to diagnose a patient's heart condition by only looking at their skin. We must rely on indirect evidence on subtle clues. The Juno mission has used its microwave radiometer to peer deeper beneath the clouds than ever before, giving us our first tantalizing glimpses of the storm's roots. Early data suggests the Great Red Spot is incredibly deep, extending hundreds of miles down far below the cloud base where sunlight penetrates. This supports the idea that it is connected to the deeper dynamics of the planet. But measuring a change in that connection, a subtle weakening of a heat plume over decades, is at the very edge of our current technological capabilities. It remains a ghostly yet compelling possibility. The storm may not be dying because of external attacks or shifting winds, but because its ancient lifeline to the planet's fiery heart is slowly being severed. It is being starved from below. There is, however, a fourth and final suspect, one that requires no external assassins or internal failures. Perhaps the Great Red Spot is simply dying of old age. This is the theory of energy dissipation, the idea of a grand, majestic and inevitable unravelling. Every physical system in the universe trends towards disorder. A storm, even one of Jupiter's scale, is a highly ordered structure. It takes an immense amount of energy to maintain that structure against the relentless pull of entropy. For all its existence, the Great Red Spot has been fighting a losing battle. It sheds energy in countless ways. It radiates heat out into the cold of space. Its colossal winds create turbulence, spawning countless smaller eddies and whirls that bleed away momentum like foam dissipating from a crashing wave. There is friction, however tenuous, with the surrounding atmospheric layers. Every single second for at least 350 years, the storm has been leaking energy. For a long time, the energy it gained either from consuming smaller storms or from that deep heat plume was greater than or equal to the energy it was losing. The system was in a state of equilibrium, or at least a very slow decline, but balances can be tipped. Perhaps we are now witnessing the point where the scales have definitively shifted. The energy losses have begun to consistently outpace the energy gains. The storm is running on a deficit. It is consuming its own vast but finite reserve of angular momentum. According to this hypothesis, there is no single dramatic event, no sudden change in Jupiter's climate that is killing the storm. Instead, we are merely witnesses to the final act of a process that has been unfolding for centuries. The storm is not being murdered, it is succumbing to a natural cosmic senescence. Its circular shape is becoming more oval, its winds are slowing, and its colour is fading because it no longer has the energetic youth to maintain its former glory. It is a cosmic gyroscope that was set spinning billions of years ago, and after an impossibly long run, the friction of its existence is finally bringing it to a halt. This idea is both elegant and melancholy. It suggests that nothing, not even a storm larger than our planet, can last forever. So we are left with a gallery of suspects, a scientific puzzle of immense proportions. Is it the constant harassment from smaller cannibalistic storms, tearing the giant apart piece by piece? Is it the subtle, treacherous shifting of the great jet stream, starving the storm of its rotational energy? Is it a weakening of the planet's own internal furnace? A failing of the deep engine that gives the storm life? Or is it simply the inescapable process of aging? The slow, quiet fizzle of a system finally running out of steam? The truth is, these hypotheses are not mutually exclusive. It is incredibly likely that a combination of these factors is at play. Perhaps a slight weakening of the internal heat flow made the storm more susceptible to attacks from smaller vortices, while a concurrent shift in the zonal jets prevents it from recovering its lost momentum. It could be a perfect storm of circumstances, a conspiracy of physics leading to the demise of a solar system icon. Untangling these threads is one of the greatest challenges in modern planetary science. We are attempting to understand the meteorology of a world so alien it defies our terrestrial intuition. The physics are governed by a dizzying interplay of Coriolis forces from its rapid rotation, deep convection magnetic fields, and atmospheric chemistry we are only beginning to comprehend. Our models are sophisticated, but they are approximations of a reality far more complex than we can yet simulate. Each new piece of data from Juno, each new observation from Hubble, adds another clue to the mystery, sometimes clarifying the picture and sometimes deepening the enigma further. We are standing on the shore of a vast ocean, watching a titanic whirlpool slowly unwind and desperately trying to understand the unseen currents moving in the dark abyss below. To find the answer, to truly know why the giant is falling, we cannot remain on the shore. We must find a way to map those currents, to take the planet's pulse, to listen to the whispers from its deep interior. We have to get closer, to look deeper, to deploy the full power of our ingenuity. Because in solving the mystery of the Great Red Spot's decline, we will learn not just about the fate of a single storm, but about the very forces that govern the evolution of all planets, including our own. And so, after centuries of distant observation and decades of tantalizing flybys, we finally brought the full power of human ingenuity to bear on this colossal enigma. We sent our emissary Juno not merely to look, but to plunge its senses deep beneath the swirling crimson cloud tops. For all our theories, for all the elegant mathematics spun in the quiet solitude of our offices, we were still grappling in the dark. The shrinking was a fact, an undeniable observation etched in the annals of astronomy, but the why and the what next remained ghosts in the machine. We needed to understand the storm's heart, its hidden engine, before we could ever hope to write its final chapter. The question that hung in the void between worlds was no longer just about its size, but about its soul. Was this a magnificent ancient king in its death throes, or was it a titan undergoing a profound misunderstood metamorphosis? Juno's instruments, particularly its microwave radiometer, gave us the first definitive answer, and it was a revelation that shook the very foundations of planetary science. The Great Red Spot was not some shallow atmospheric stain, a meteorological veneer painted upon the surface. It possessed a depth so profound it defied all previous models. Imagine an iceberg floating in the ocean. What you see above the water is only a fraction of its true mass. The Great Red Spot, we discovered, is a cosmic iceberg of unimaginable scale. Its swirling vortex, the part we see, plunges downwards, extending more than 300 miles, perhaps even deeper into the crushing pressures of Jupiter's interior. 300 miles. That is farther than the distance from the surface of the Earth to the International Space Station. This single discovery transformed our entire perception of the storm. It wasn't a weather event. It was a fundamental feature of the planet itself, a structure with roots that tapped directly into the terrifying furnace of Jupiter's deep atmosphere. This unfathomable depth provides the first crucial clue to its ultimate fate. A shallow storm is ephemeral, at the mercy of the shifting winds around it, easily starved of energy and torn apart by the relentless jet streams. But a storm this deep is a different beast entirely. It is a self-sustaining heat engine, a gravitational anchor in a sea of chaos. Its roots dredge up hot gases from below, feeding the storm's core, while cooler gases from its upper atmosphere are dragged down along its periphery. Juno's gravity science experiments confirmed this vertical motion painting, a picture of a system in constant violent circulation, a celestial pump operating on a planetary scale. This is the source of its tenacity. The red spot has survived for centuries, not because it is placid, but because it is ravenous, continually devouring smaller storms that wander too close, and drawing immense power from the thermal gradients between the planet's scorching interior and its frigid cloud tops. Its longevity is a testament to its connection to this hidden reservoir of energy. With this new three-dimensional understanding, the scientific community has converged on three primary scenarios for the storm's future, each a dramatic possibility, each supported by compelling pieces of the puzzle. The first and perhaps most intuitive is the scenario of a great fading. This hypothesis posits that the storm is quite simply running out of fuel or losing the battle against its environment. The evidence is plain to see the relentless shrinking of its east-west diameter, the paling of its once vibrant crimson hue to a subdued orange, and the increasing frequency of flaking events where massive streamers of red material are peeled away from its edges by the fierce surrounding jet stream. Proponents of this theory argue that the storm's deep engine, while powerful, may not be infinite. Perhaps subtle changes in Jupiter's deeper atmospheric currents, a slow alteration in the planet's internal heat flow, have begun to starve the vortex. In this vision of the future, the red spot will continue to shrink and fade, its winds slowly decelerating over the coming decades, until it becomes just another anonymous white oval, eventually dissipating entirely its legacy, swallowed by the turbulent atmosphere that birthed it. It would be a quiet, drawn-out death, a slow dimming of the solar system's most magnificent fire. But a second, more complex possibility has gained significant traction, fueled directly by Juno's discovery of the storm's incredible depth. This is the scenario of stabilization through transformation. It suggests we are not witnessing a death but a fundamental change in character. Think of a spinning figure skater. When they pull their arms in, their rotational speed increases dramatically due to the conservation of angular momentum. Some atmospheric scientists believe we're seeing the same principle at play on a planetary scale. As the storm's horizontal extent shrinks, it may be stretching vertically, its structure changing from a wide, relatively flat pancake into a taller, more compact and more intense cylinder. The energy that was once spread out over a vast area is now being concentrated into a smaller footprint. In this scenario, the shrinking is not a sign of weakness, but a sign of tightening of the storm becoming more dynamically efficient. Its winds, far from slowing, could even be accelerating within its core. It would survive not as the sprawling giant of yesteryear, but as a smaller, more focused and perhaps even more violent vortex, a permanent fixture stabilized by its own concentrated power. It would not die, but would instead evolve into a new, more sustainable equilibrium, a perpetual hurricane for a new age. Then there is the third and most spectacular potential fate, a cataclysmic fragmentation. The Great Red Spot is not an isolated entity. It is a giant navigating a treacherous, violent highway of competing storms and powerful jet streams. We have seen it collide with and absorb countless smaller vortices over the centuries. But what if it were to encounter another storm of sufficient size and opposing spin? Or what if the sheer forces from the surrounding jets, which are already peeling away its edges, were to intensify? The flaking events we observe could be a prelude to a much larger structural failure. In this scenario, a powerful enough perturbation wouldn't cause the storm to fade, but to shatter. Imagine the Great Red Spot breaking apart not into atmospheric dust, but into multiple smaller red spots. A dynasty of storms, each carrying a piece of its parent's angular momentum, would be scattered across Jupiter's southern hemisphere. These offspring would be less stable, more transient, doomed to wander the planet and eventually dissipate. But for a time, Jupiter would be adorned not with one great spot, but with a family of crimson jewels. It would be a violent, explosive end to its singular reign, replacing a monarchy with a fleeting, chaotic republic of smaller but still potent maelstroms. To adjudicate between these dramatic possibilities, a slow fade, a dynamic stabilization, or a catastrophic shattering, scientists have turned to one of humanity's most powerful tools, the supercomputer. They are building digital Jupiter's virtual laboratories of immense complexity, where the laws of physics can be run forward in time. Into these simulations, they pour every piece of data we have gathered, the wind speeds from Voyager and Galileo, the atmospheric composition from Hubble, and most critically, the new information on the red spot's temperature structure and three-dimensional depth from Juno. They create a digital twin of the storm, a ghost in the machine that swirls and rages according to the very same fluid dynamics that govern the real thing. It is a monumental undertaking, an attempt to replicate a system so vast and chaotic that it strains the limits of our computational power. These models are the closest we can come to running the experiment to fast-forwarding the planet itself to see which future will prevail. And the initial verdicts from these digital realms are beginning to offer a tantalizing synthesis. The simulations consistently show that the storm's depth is its greatest asset for survival. Models that treat the red spot as a shallow feature see it torn apart by jet streams in mere years, but when its true 300-mile depth is programmed in the storm, becomes shockingly resilient. The digital vortex powerfully resists disruption, healing itself from simulated collisions and holding its form against shearing winds that would obliterate a lesser storm. These results lend powerful weight against the idea of a sudden imminent death or fragmentation. The storm's deep-seated nature gives it a thermal and dynamic inertia that is difficult to overcome. The most sophisticated models, running for simulated decades and centuries into the future, suggest a path that combines elements of the first two scenarios. They predict that the shrinking will likely continue, driven by a complex interplay of energy loss at its edges and subtle shifts in the currents that feed it. However, they do not predict its complete disappearance, at least not on any human timescale. Instead, the simulations point toward a very long, very slow decline into a more stable circular state. The storm, having shed its sprawling oblong shape, will settle into a more compact form. It may continue to shrink, but at an ever-decreasing rate, eventually reaching a point of equilibrium, where the energy it radiates away and loses to friction is perfectly balanced by the energy it dredges up from Jupiter's interior. It would become a permanent, though diminished, feature of the planet. So the answer, emerging from the synthesis of Juno's observations and our most powerful simulations, is not a simple yes or no. The Great Red Spot is not dying in the way a living creature does. It is evolving. The Titan of the 19th century is gone, and the giant of the 20th century is fading. What will take its place is something leaner, more concentrated, and perhaps in its own way, more perfect. It is a slow, majestic transition from a sprawling empire into a fortified, enduring kingdom. What you're witnessing is not the agony of a dying storm. You are seeing the very process of planetary evolution playing out on a timescale we can comprehend. We are privileged observers of a fundamental shift in the state of the solar system's largest and most powerful atmospheric phenomenon. The storm is responding to its changing environment, shedding its excess mass, and settling into a new form that could grant it life for thousands of years to come. This is no longer a simple question of survival, but a deeper inquiry into the very physics of chaos and order. The Great Red Spot is teaching us that even the most violent systems in the cosmos seek a kind of balance, a state of sustained dynamic equilibrium. It is a lesson in resilience, a story written in wind and heat and pressure across a canvas 100,000 miles wide. The real mystery we're now beginning to understand was never if it would die, but what it would have to become in order to live. And as we continue to watch, to model and to learn, we are forced to confront an even more profound question. If a storm can adapt and evolve on such a colossal scale, what other secrets about the nature of persistence and change are hidden in the atmospheres of the giants that drift through the unending cosmic night? After a journey across centuries of human curiosity and hundreds of millions of miles of empty space, we arrive here at the edge of an ending. We have stood on the shoulders of giants from Cassini and Hooke, who first sketched a curious blemish on a distant world, to the engineers of our time who hurled avatars of our ambition into the dark. We have watched a storm bigger than our own planet, a celestial hurricane that has raged for at least as long as our modern civilization has existed, and we have seen it begin to die. Its story, we now understand, is not merely the chronicle of a weather pattern. It is a profound lesson in the nature of time, the mechanics of creation, and the beautiful, brutal impermanence of everything in the cosmos. What the Great Red Spot has given us in its long, magnificent life, and its slow, inexorable decline, is something truly priceless, a laboratory on a scale we could never dream of building. Here in this swirling vortex of hydrogen and helium, nature has been running an experiment for us for over 300 years. An experiment in fluid dynamics, in atmospheric physics, and in the very endurance of organized systems against the universe's relentless push towards chaos. On Earth, our most powerful hurricanes are born from the warm breath of our oceans, drawing their strength from that thermal reservoir. They are powerful, yes, but they are fleeting. They make landfall, and cut off from their energy source, they gasp, sputter, and dissolve into rain within days or weeks. They are creatures of the sea and the shore. Jupiter's Titan, however, is a different beast entirely. It has no solid surface to grind it down, no continents to break its stride. For centuries we were baffled by its longevity. What was its secret? How could a storm, an entity defined by its turbulent energy, maintain its identity for so long? The answer unveiled by the intrepid flybys of Voyager, and the deep penetrating gaze of Juno was as elegant as it was violent. The Great Red Spot was not simply existing, it was feeding. We watched mesmerized as it consumed smaller, younger storms, pulling them into its colossal embrace like a gravitational predator. Each ingested vortex was a transfusion of energy, a sacrifice that donated its own angular momentum to the aging giant, helping it fend off the dissipative forces that sought to tear it apart. Observing its slow transformation from a grand oval to a more circular shape has been like watching a star evolve in fast forward. This shrinking is not just a cosmetic change, it is a fundamental shift in its metabolism. As its footprint on Jupiter's cloud tops has contracted, its internal dynamics have been forced to adapt. Juno's microwave radiometer peeling back the high-altitude ammonia clouds has shown us that the storm is not a shallow puddle, but a terrifyingly deep atmospheric pillar, its roots plunging hundreds of miles into the planet's crushing interior. We have learned that its structure is far more complex than a simple cyclone. It is a towering, self-sustaining heat engine dredging up warmth from Jupiter's core and radiating it into space, a process that helps drive its furious winds. And as it shrinks, this engine is being retuned right before our eyes. The wind speeds at its sharpened perimeter have actually increased a paradoxical intensification as the storm's overall energy winds down. It's like a spinning figure skater pulling their arms into spin faster just before they glide to a stop. This phenomenon, observed in real time, has sent theorists scrambling to refine their models. Every new image, every fresh data point on its temperature composition and velocity provides a crucial test for the mathematical equations we use to understand not just Jupiter, but all planetary atmospheres. The laws of physics are universal. The principles that govern the flow of gas and the transfer of heat in that Jovian vortex are the same ones that operate inside the engine of a star in the accretion disk around a black hole, and in the nascent cyclones that brew over Earth's own tropical waters. The Great Red Spot has been our grand unified field guide to the weather of the worlds. Its saga forces us to confront a truth that is both humbling and strangely comforting, that nothing, not even a storm that could swallow our world whole, is forever. We humans, with our fleeting lifespans, have a tendency to see the cosmos as a static painted backdrop. We look to the sky and see permanence. But this is an illusion born of our own ephemeral nature. The universe is a place of constant, relentless, and often spectacular change. Stars are born in fiery nurseries and die in cataclysmic explosions. Galaxies collide and merge in a gravitational dance that plays out over billions of years, and planets which we might imagine as stoic and unchanging are living, breathing worlds with dynamic climates and evolving features. The slow fade of Jupiter's iconic spot is a tangible, visible reminder of this cosmic flux. It is a lesson written in the clouds of another world, teaching us about the fragility that coexists with grandeur. For generations, it was a symbol of permanence, the Great Red Spot, a name that implied an eternal and unchanging nature. Its shrinking forces us to reconsider. If a system this vast, this powerful, this long-lived can wither away, what does that say about the more delicate systems we see across the universe, including the one we inhabit here on Earth? It offers us a cosmic perspective on our own struggles with a changing climate. While the forces driving Jupiter's storm are internal, born from the planet's primordial heat, the lesson is one of balance. We see how a complex atmospheric system, stable for centuries, can be tipped into a state of irreversible decline by subtle shifts in its energy budget. We are watching a planet's climate feature respond to changing conditions, a process we are now grappling with ourselves. Jupiter, in its immense and alien way, holds up a mirror. It shows us that planetary atmospheres are not static fixtures. They are intricate, sensitive, and subject to profound transformations over time. Understanding the physics of the Great Red Spot's decay, how its energy dissipates, how its chemistry alters, how its structure fails, sharpens the very tools we need to predict the future of our own world's climate with greater accuracy. This entire epic of discovery is also a profoundly human story. It is a testament to our species' unquenchable desire to know, to understand, to venture beyond the horizon. Think of the patience it required. Generations of astronomers squinting through eyepieces, painstakingly sketching the storm's shape and position passing their logbooks down to their students. They were laying a foundation of data brick by painstaking brick without any hope of seeing the final cathedral themselves. They were the sentinels, the faithful watchkeepers of this distant storm, their combined observations forming an unbroken chain of vigilance stretching back to the dawn of the Enlightenment. Then came the age of robotic explorers, the crescendo of this centuries-long overture. We built machines of astonishing complexity, imbued them with our scientific curiosity, and flung them across the solar system on trajectories calculated with breathtaking precision. These probes, Pioneer, Voyager, Galileo, Juno, were more than just instruments. They were extensions of our own senses. Through their cameras, we gained a perspective that had been denied to every human who had ever lived. We soared over the crimson clouds, we plunged through belts of lethal radiation. We listened to the planet's strange magnetospheric music. We became for a time citizens of the Jovian system. This quest was driven by thousands of individual scientists and engineers from all over the world united by a common purpose. They are the unsung heroes of this story. The ones who wrote the millions of lines of code, who designed the heat shields, who triple-checked the telemetry, who stayed up through the night, hearts in their throats, waiting for a faint signal to arrive from 500 million miles away, confirming that their creation had survived another perilous maneuver. Their dedication, their collaborative spirit is perhaps as inspiring as the storm itself. They prove that when we work together, driven by curiosity and a shared hunger for knowledge, there are no limits to what we can achieve. We can touch other worlds. We can decode the secrets of the sky. We can watch a world change before our very eyes, and so we stand at a precipice peering into an uncertain future. What will become of Jupiter's most famous feature? The data suggests its decline is terminal, but the cosmos is full of surprises. Perhaps it will not vanish entirely. Some models predict it could stabilize as a much smaller but still persistent vortex, a great red circle, perhaps a shadow of its former glory. Or maybe it will break apart its energy, dissipating into the surrounding jet streams, its reddish chemical signature smeared across a band of latitude, until it is unrecognizable like a drop of ink dissolving in water. There is also the tantalizing possibility that this is a cyclical process. Jupiter is a storm factory. Perhaps decades or centuries after the current spot fades, to an atmospheric ghost conditions will become ripe for a new megastorm to be born, a successor to the throne, rising from the depths to begin the cycle anew. We simply don't know. And that is the most exciting part. The story is not over, our watch continues. The ever-watchful eyes of Hubble and the James Webb Space Telescope, alongside ground-based observatories, will carry on the vigil started by Cassini so long ago. Future missions already on the drawing board may one day send even more advanced probes to orbit the gas giant, or perhaps even to brave a descent into its turbulent depths. The end of one mystery is always the beginning of another. The questions will keep coming, and as long as they do, we will keep seeking answers. As we pull our gaze away from Jupiter, we carry its lessons with us. The Great Red Spot was more than just a storm. It was a cosmic timepiece marking out a different scale of existence. It was an anchor in the swirling chaos of the solar system's largest planet, a familiar face in an alien landscape. Its life has been a silent, majestic epic, a drama of physics and chemistry playing out on the grandest possible stage. To have been alive at the moment of its twilight, to have possessed the technology and the will to witness its transformation, is a remarkable privilege. We are the generations who saw the Titan falter. The light from that storm, the photons that carry its image to our telescopes, takes over 40 minutes to cross the gulf of space and reach our eyes. The light you see from it tonight left Jupiter before you started watching this program, and that light will not stop at Earth. It will continue its journey outwards, racing past our planet and into the interstellar deep. Long after the storm itself has vanished for thousands, for millions of years, that final fading light will travel on, carrying the ghost of the Great Red Spot through the cosmos. A faint reddish echo moving at the universal speed limit, an eternal testament to the magnificent, beautiful and transient wonder that once churned in the atmosphere of Jupiter, and to the curious species on a small blue world who looked up and for a short while were able to watch